Right, so we talked, I showed you that powers of 10 video, which goes into the size scales of things. So in astronomy, we tend to round off a lot. So a human body, we think of it about a meter, a couple of meters, something like that. And then we move into mountains, and mountains are kilometers. You know, oceans are bigger than kilometers usually. Continents are thousands of kilometers. And then we hit the Earth's diameter, which is about 13,000 kilometers. So its radius is then about 6,500 kilometers roughly. Then the next object we're talking about here is the Sun with a diameter, actually that's supposed to be radius, of a little over 1 million kilometers, about 1.4 million kilometers. Okay? The Earth-Sun distance is 140 million kilometers. So when we look at the Sun, we're seeing something that's about 100 times larger than the Earth. The Sun itself is about 100 times larger than the Earth. If you think of it in terms of volume, if you remember how volume works for a sphere, it's proportional to the cube of the radius. So with the Sun being 100 times larger, that's we would take 100 and cube it and get 1 million. So you could fit 1 million Earths inside the Sun, or you could string 100 Earths across the interior of the Sun. But anyway, then that's a gigantic object, obviously. Although we'll see there are stars that are unbelievably bigger than the Sun, and then of course even larger objects than that, like we call star clusters and galaxies. But the Earth-Sun distance is about 100 times larger than the Earth, than the Sun itself. So the Earth-Sun distance we call the astronomical unit. That's about 100 solar diameters, an incredibly huge distance of about 140 million kilometers. And that's Earth's average distance from the Sun. We call it the astronomical unit. It's Earth's average distance from the Sun. And I say that because Earth's orbit is not exactly circular. It's actually very close to circular, but there's a little bit of a wobble or eccentricity in Earth's orbit. So there's actually a slight variation of Earth's distance from the Sun because of that slightly elliptical shape of the orbit, but it's pretty close to circular. Now, when we're talking about distances to the stars, we start introducing a new unit called a light year, which is the distance light travels in a year. And because light has such an incredibly high velocity, a light year is around 10 trillion kilometers or so. 10 trillion kilometers. And that's not even the distance to the next star. It's about 3.5 light years away, roughly. So if you start comparing things here, I mean, a light year compared to an astronomical unit, okay, an astronomical unit seems huge, 140 million kilometers, right? But actually, that's roughly about 1 million times smaller, or about 100,000 times smaller than a light year. So as spread out and huge as our solar system seems, it's microscopic compared to the distance just to the next star, let alone across the galaxy or something like that. Now, we are going to be using scientific notation here and there in this course because we don't like to write lots and lots of zeros. So we use scientific notation, which indicates the number with an antissa and an exponent here. So 140 million could be written as 1.4 times 10 to the 8th power, which is a 1 followed by 8 zeros. So this makes calculations easier, and we'll do some example calculations where we actually have something to calculate a little later in the course. But what we do tend to use scientific notation because it's just ridiculous to have to write down all the zeros that you have to use otherwise. All right, so again, the astronomical unit is the distance, the average distance of the Sun from the Sun to the Earth. And this is not to scale. Many images that I show and that you see in the book, of course, are not to scale because the problem is there's so many scales that are vastly different from each other in astronomy. So, for example, this astronomical unit, Becker? The astronomical unit is supposed to be 100 times larger than the Sun. So this is not, right? And this is only like about 5 times larger than the Sun. 5 times larger than the Sun on this scale. And the Sun is supposed to be 100 times larger than the Earth, but it's not. So you can't do this because if you based everything on the Earth's size, then compared to the astronomical unit, you wouldn't even see the Earth. There'd just be a dot, right? And even the Sun would only be 100th of this radius, so it's not useful to do it that way. But the point of this panel is just that the astronomical unit is the average distance between the Sun and the Earth. Okay, so we have 15,000 kilometers or so for the diameter of the Earth. By the way, this panel has a funny notation on the bottom. There's a V in red, which indicates this is a visible light image. So in the book, throughout the course, we'll be looking at images that were derived using data in different wavelengths. Not necessarily good old visible light, but sometimes infrared light, which is like heat radiation. You know, you can image with heat radiation. You have your heat goggles and whatnot, so you can make an image that way. You can actually also make an image out of radio waves, and those types of radiation are lower energy than visible light. But there's another side to the electromagnetic spectrum where the wavelength, as indicated here, gets smaller, and we run into higher energy forms of radiation like ultraviolet radiation, X radiation, and gamma radiation. And those are actually harmful, but they're very helpful in astronomy because they teach us about very extreme environments with high temperatures. All right, so looking at the sun with a diameter of about 1.5 million kilometers, again invisible. Okay, we just see a pretty featureless disk, but there are sun features, sunspots, which we'll talk about. Now here we've gone a huge scale up to the size scale of a galaxy that probably looks a lot like ours. This is the Andromeda Galaxy, which we think probably looks a lot like our Milky Way galaxy. We can't know that for sure because we can't get outside our Milky Way galaxy and actually observe it. Because to do that, I mean, look at the size of this thing. It's about 100,000 light years across. We only have the technology to travel through space at maybe, I don't know, 10,000th of the speed of light now or something like that. So it would just take millions of years for us to get outside and take the photo. So it's not really, even though paparazzi aren't, well, I think they may be working on the technology, but they're not really ready to implement that yet. They have to have generations of paparazzi in space to survive the journey, get the photo, and then come back and harass the what do you call the famous people? The celebrities. But they'd all be dead, so it really wouldn't matter. It would be millions of years later. Now, as we go beyond the scale of a single galaxy, we get into even larger entities, which are clusters of galaxies that are gravitationally bound to each other. When you get to scales like this, about 1 million light years across this cluster of galaxies, it's just completely mind-boggling how something like this could form. So you got to realize that they're being held together by their mutual gravity, the force of gravity. But even the force of gravity only travels at the speed of light. So if something happens in one of these galaxies or it moves a little bit, the other galaxies won't even feel the force for 1 million years. I mean, that's unbelievably spread out and gigantic, this kind of structure. So it just makes it all the more mind-boggling that something like this can actually form, when even the forces are delayed over such long time scales, forces that actually hold the structure of the thing together. Now, somebody asked me how we know how large the universe is last time, and I mentioned that we see structures up to the largest scales that we can observe. And then beyond that, we really don't know, except that one can say that we're looking farther and farther back in time. So when we look back so far that we see galaxies in their infancy and very young stars, then we basically know we've looked back the whole lifetime of the universe. And that actually is the way we know the size of the universe, is by using the time that it takes to see objects from the distant past. Okay, so the hierarchies go on and on. There's billions of stars in a spiral galaxy. There may be billions of actual, well, there's billions of stars in a spiral galaxy. There's no doubt billions of galaxies in the universe that we can see. Now, this is another little video, which is a lot of very dramatic music, not too long, but it actually gets into the size scale thing. And the thing I like about it is it starts to show you the size of our star, the sun, compared to other stars. Now, the sun is huge, 1.5 million kilometers across, but it's completely dwarfed by some really monstrous stars that are residing in our galaxy, and other subdivisions, if you will, of our galaxy. Kind of cute. So actually already you can see something kind of interesting. That's our moon over there. Mercury's not too much bigger than our moon. So we're already seeing, kind of learning a little bit about our solar system here. That's the planet Mercury, the closest planet to the sun. It's just moderately bigger than our own planet. Stop. Feel the urge to drone on about this just a little bit more. Here we have Venus, sort of the way it really looks, and here we have Earth. Venus and Earth are pretty similar in size, Mars is quite a lot smaller. Mars is only about half the size of Earth, something that a lot of people don't realize. A lot of people tend to think of Mars as being a twin of the Earth. Venus is nearly a twin of the Earth, but Mars isn't. It's a dwarf planet compared to Earth. And we'll see that has a lot to do with the way Mars has formed. And for example, the reason there's no geologic activity on Mars, it's cooled off rapidly because it's a smaller planet. No falling asleep, despite the soundtrack. Okay, so now we're getting to the gas giant planets, Neptune, Saturn, Jupiter. So Jupiter is about 10 times larger than the Earth. And here we have the Sun about 10 times larger than Jupiter. So again, we're going up by magnitude here. Now we're getting the bigger stars. Serious about this, but that star right there actually is the brightest star we can see in our sky. It's not too far from the constellation of Orion, if anybody's familiar with Orion, the hourglass-shaped constellation. It's sort of off to the lower left of Orion. A very bright, it's pretty close, and it's bright, making it the brightest star in the sky, other than our own sun, of course. Now we get into giant stars. Notice how the sun's starting to shrink away here. Is actually the largest known star in the universe that we know of. It's about 1,000 times larger than the sun. It's not as much more massive as you might think. It's actually about 17 times the mass of the sun. So it's 1,000 times larger in radius, but it's only about 17 times the mass. It's very low density, but it's a regular energy-producing star, and it's just it would actually, if we put this in our solar system, the star itself would reach out past Jupiter. So everything would just be, about half the solar system would be inside this monster right here. Huh? Stop the plug-in? I don't know. Not sure. What happened? It delayed for a moment. Okay. Come back. Since they changed the operating system, I don't know how to do CPR on this thing anymore. So. Come back, baby. All right. You can deal with this. We're trained.
Try refreshing it.
Task manager. F. Flash player. Who's that? Firefox 2. Yeah. Kind of crashed. See? Not happy. Okay. It's a sad one. Yeah.